This is Mrs. Amiette, and we are looking today at the speed and velocity worksheet. So up here at the top, we've got some need-to-know information. For this worksheet, what you need to know is the formula. And here's the formula. Velocity is equal to change in distance over change in time. And remember, this is the formula, and the variables are what make up the formula. So v is a variable representing velocity. Delta d is a variable representing change in distance. Delta t is a variable representing change in time. And let's look at example A. If an odometer reads 0 at the beginning of a trip and 36 kilometers at a half hour later, what is the car's average speed in meters per second? So we're looking for speed, and to find speed, we can use the velocity formula. So velocity is given by the change in distance over the change in time. And it tells us that at 0, we have 0 distance, but after 36 kilometers, we have 36 kilometers. So the total change in distance is going to be 36 kilometers. So we'll put that in for distance. The total change in time is a half hour. So for time, we can put 0.5 hours. And this would be good enough, but the problem asks us to convert it to meters per second. So we have to go back to our conversion equalities, and we're going to convert kilometers to meters. So there are 1,000 meters within a kilometer. So we're going to put 1,000 meters up here in the numerator and 1 kilometer in the denominator. Kilometers will cancel out, and now we're in meters. For our second conversion, we're going to go from hours to seconds. And we know that in 1 hour, we have 60 minutes. And in 1 minute, we have 60 seconds. And that'll take care of our second conversion. So now we can cancel out hours, cancel out minutes, and we are now in meters over seconds. Multiply across the top, and you're going to get 36,000 meters. Multiply across the bottom, and you're going to get 1,800 seconds. Plug that into the calculator, and the answer you should get is 20 meters per second. Go ahead and put a box around it so it's easy for us to find when we're grading. Example B. On May 28, 2000, Juan Montoya became the first Colombian citizen to win the Indianapolis 500. Montoya completed the race in a time of 2.98 hours. What was Montoya's average speed during the 500-mile race? Again, we're looking for speed. We can use the velocity formula. Velocity is given by change in distance over change in time. For this race, the total distance was 500 miles. And the total time was 2.98 hours. This one is simple. We just divide. And remember, when you're putting this into the calculator, put the top number into the calculator first, divided by the bottom number. And what you should get is 168 miles per hour. Example C is a bit more difficult, and I like this example because we can use it to review graphing. So I put a grid for a graph in here. Let's read the problem. Tiffany, who is opening in a new Broadway show, has some limo trouble in the city. With only 8 minutes until curtain time, she hails a cab and they speed off to the theater down a 1,000-meter long, one-way street at a speed of 25 meters per second. At the end of the street, the cab driver waits at a traffic light for 1.5 minutes and then turns north onto a 1,700-meter long traffic-filled avenue on which he is able to travel at a speed of only 10 meters per second. Finally, this brings them to the theater. Does Tiffany arrive before the theater lights dim? Draw a distance versus time graph of this situation. Alright, so what we've got going on here is 3 time intervals. So we're going to have delta t number 1, where Tiffany is speeding down a 1,000-meter long one-way street at 25 meters per second. We'll use that information to get time number 1. Then we have delta t number 2, and this time interval involves Tiffany waiting for 1.5 minutes. Then we have time interval number 3, delta t number 3. This time interval we will find using 10 meters per second as Tiffany travels down a 1,700-meter long avenue. Now, we're going to solve for time, so we're going to put our formula here. Velocity equals the change in distance over the change in time. We need to find time using this formula. So to find time, we're going to rearrange the variables algebraically. To do that, I'm going to get time out of the denominator. I can't solve for time when it's in the denominator. I have to get it up into the numerator. So my first step is to multiply each side by time. The rules of algebra tell us that whatever you do on one side of the equation, you have to do on the other side of the equation. So if I multiply by time over here, I have to multiply by time over here. I'm going to cancel out time and rewrite the formula. Now I've got delta d, change in distance, is equal to the change in time times velocity. And again, I'm solving for time. So I have to get rid of velocity. To get rid of velocity, if we're multiplying, I have to divide out velocity. So I'm going to divide out velocity. The rules of algebra tell us whatever I do on one side of the equation, I have to do on the other side of the equation. So I'm going to divide out velocity here as well. Now I'm going to cancel out velocity, rewrite the equation, and we've done it. The change in time is going to be given by the change in distance over velocity. All right, let's apply this to each of our time situations. For the change in time number 1, Tiffany is traveling 1,000 meters at 25 meters per second. So our change in distance is 1,000 meters. And our velocity is 25 meters per second. Now I can cancel out these meters, and for the unit of seconds, I have a denominator within a denominator. Whenever you have a denominator within a denominator, that denominator becomes the numerator. 1,000 divided by 25 is going to give us 40. And the unit on that is going to be seconds. For time interval number 2, Tiffany's waiting at a traffic light for 1.5 minutes. So on this one, I don't have to apply my formula, I just have to convert minutes. So I've got 1.5 minutes, and I need that in seconds. So I'm going to put that over 1, and I'm going to convert. I know that there are 60, whoops, made a mistake. I know that there are 60 seconds in 1 minute. Cancel out minutes. 1.5 times 60 seconds, and that'll give us 90 seconds for time interval number 2. For time interval number 3, we've got Tiffany traveling down a 1,700 meter long avenue at a velocity of 10 meters per second. So again, we're going to use our formula solved for delta t. Time interval 2 is going to be given by 1,700 meters divided by 10 meters per second. We can resolve these units again, cancel out meters, a denominator within a denominator becomes a numerator. 1,700 divided by 10, and we've got 170 seconds. So now, I know the total time. The total time is going to be given by 40 seconds plus 90 seconds plus 170 seconds. And the total is 300 seconds. So now our question is 300 seconds within 8 minutes? Well, let's find out. We're going to put 300 seconds over 1. And we know that there are 60 seconds in 1 minute. We can cancel out seconds here, and 300 divided by 60 is 5 minutes. 5 minutes is less than 8 minutes. So from that we can conclude that yes, Tiffany made it on time. Now let's graph this situation. So on a graph, you always want to have a title, and when you're doing your lab work, this is very important. Your graphs will be graded, and one thing we'll be looking for is that you put a title on that graph. You're going to create your graphs. So we're going to call this a distance versus time graph, and I'm abbreviating it to fit in this space. We have to decide which variable is the dependent variable and which variable is the independent variable. So in this case, time is the independent variable. Whenever you label the graph, you're going to put the label there, and then you're also going to include the unit. So time in this case is measured in seconds. On the y-axis, we're going to put distance. And again, when you're labeling the axes on your graph, you have to include the unit. So in this case, it's going to be meters. You have to choose an appropriate scale for the graph so that the information, the data, takes up most of the space. This one works out perfectly. Time goes from 0 to 300 seconds, So we can start at 0 and scale it in increments of 100, 100, 200, 300. So the total time that elapsed is 300 seconds. Distance works out nicely too. The total distance that Tiffany traveled is 1,000 meters plus 1,700 meters, so that's 2,700 meters. So we can scale this graph in increments of 1,000. So we'll go 1,000 meters, 2,000 meters, and 3,000 meters. Okay, so the first interval was 40 seconds. So halfway to 100 seconds is 50. We'll back it up a little bit and say that that's 40 seconds. And in 40 seconds, Tiffany was able to travel 1,000 meters. So our first data value goes right here. The next time interval was 90 seconds. So we've got 60 plus 30, and we can put our next data value right here. Tiffany traveled no distance in the second time interval. The third time interval was 170 seconds. So it's going to take us all the way to 300 seconds. But in that time, she was able to travel 1,700 meters. So we'll go up 1,000 meters and then beyond halfway to 3,000. So right here is about 1,700 meters. In this case, we're just plotting known data. So we don't need a best fit line. Many of your experiments are experimental, and you'll put in a best fit line. But in this case, we just plot the data points. And there we have our graph of the situation. Let's look at the next page. All right, these are your practice problems. Number 1 should be fairly easy for you to plug in. You just plug into the velocity formula. Number 2, also plug into the velocity formula, but notice you're going to have to convert it to meters per second. On number 3, the question is asking you, how long will it take for you to get to a college campus? You're given 230 miles, that's distance, and you're given 60 miles per hour, that's velocity. So in this case, you're going to solve for time. Just like we did in example C with Tiffany's situation. On number 4, again, you're looking for time. How long will it take to get to your interview? So you're going to need to solve for time again. And on number 5, once again, you're looking for how many minutes. So you're going to use that time formula again. Number 6, this image is in your notes. You can compare it to another image that's in your notes to figure out what's going with this distance time graph and answer these questions. Notice there may be more than one part of the graph that applies to these situations. And on number 7 and 8, you need to determine which variable is the independent variable and which variable is the dependent variable. Remember your acronym, dry mix, to help you determine this. So there you have it. Good luck. Check your calendar for the due date.